Hello dear learners, welcome to the online course on electricity and electrical wiring. This is the second lecture of module 7 on electrical house wiring. In our first lecture, we learned that electricity is generated in power plants. The generated electricity is then transported through a network of transmission and distribution lines to locations near the consumers. From there, the power is supplied to consumers through the service mains. We discussed about the different types of distributors and service mains used by authorities to deliver the power to consumers. Lastly, we explored some of the key electrical accessories used in house wiring. Okay, now in this lecture, we will focus on the internal wiring of a house. We will cover various design aspects of single phase installation. So by the end of this lecture, you should be able to understand the layout of single phase house wiring. Then you should be able to determine the number and types of sub-circuits required for any given problem. And finally, you should be able to select the appropriate sizes of cables, accessories and protective devices. With these objectives in mind, let us begin this lecture. So, by now, we have learned that all consumers requiring electric supply are connected to the supplier's distribution line through connections or tapping points. For small and very small installations, power is supplied through low voltage distributors. These typically operate at 415 by 240 volts in a 3-phase 4-wire system. On the other hand, large consumers are supplied power at high voltages such as 6.6 kV, 11 kV or 33 kV. In such cases, the consumers have their own step-down substations. These substations convert the high voltage supply to the required voltage for their uses. You see, the power from these distributors reaches the consumer's energy meter using the service mains. From here, the internal distribution system takes over. This system carries and controls power from the meter to the switchboards. The switchboards then supply the final circuits, which in turn feeds the various loads. Now, let us explore the different types of electrical wiring arrangements used for various installations. Let's start with small installations. So when we say small installation, it normally includes consumers with low power demand, like in the range of less than 5 kilowatt. Small installations may include small residential houses, local shops, etc. Power supply for such installations is typically provided using a single phase supply. The service mains used in this case is typically a 2-core cable. So here is the image of a 2-core cable. On my right, we can see this diagram. This particular line indicates the service mains. So on one end of the service mains, we connect it to the phase and neutral of the low voltage distributor. So on one end of the service mains, we can see that it is connected to the phase and neutral of the low voltage distributor, and on other end, the service mains is connected to the input terminals of the energy meter. So here, this is the input line that we are talking about. So the energy meter is the first device in an electrical wiring. The energy meter records the energy consumed by the consumer. In small installations, single phase energy meters are used. However, earlier electromechanical energy meters were used. These meters could only measure and indicate the units consumed. However, modern smart meters offers much more functionality. Apart from the energy consumption, they can also measure and display additional parameters like voltage, current, frequency, maximum demand, tariffs and many more. So when installing an energy meter, it must be placed at a location and height that is readily accessible. This ensures convenience for noting meter readings. The meter can be enclosed in a lockable cabinet, but a glass window must be provided for visibility. Modern meters can communicate the meter readings to authorities using wired and wireless medium. So there is no need for a meter reader nowadays. Okay, so from the output terminals of the energy meter, leads are connected to a main circuit breaker. Here is the connection. So from the service mains it goes to the energy meter, and from the output terminals of the energy meter it goes to a main circuit breaker. Here in this diagram, this is the connection that we are talking about. So this main circuit breaker serves two purposes. Number one, it protects the installation from electrical faults. Number two, it acts as the main switch. For small installations, a double pole MCB of appropriate rating is commonly used as main circuit breaker. By turning it off, the entire installation can be disconnected from the supply. In earlier systems, a main switch fuse unit was used. So this is the image of a main switch fuse unit. So this unit combined a double pole switch and a fuse element. However, modern alternatives like MCB are more readable and widely used today. The main circuit breaker should be placed in a location that is easily accessible to consumers. It should not be locked or sealed inside any enclosure. After the main circuit breaker, the supply is connected to a distribution board. The DB takes power from the main circuit breaker and distributes it among various sub-circuits. So here, this is the line where the connection is given from the main circuit breaker to the distribution board. At the incoming line of the DB, normally a double pole switch like the double pole MCB or double pole isolator is typically used. So in this diagram, this is the double pole MCB which protects the incoming line. The line output from this double pole switch is fed to the inputs of single pole MCBs. So here you can see that the output of the double pole MCB are fed to the single pole MCBs. Each MCB, or that is the single pole MCB, feeds the live wire of a sub-circuit. So here we can see that this connection that we are going to see, or that we are seeing, the single pole MCBs feeds a line, and this is the live wire of the sub-circuits. We are going to talk about the sub-circuits in the upcoming slide. The neutral output from the double pole switch is connected to a neutral terminal block. The neutral wires for each sub-circuit are drawn from this block. Additionally, the distribution board provides the earth terminal block. From here, the earth wire is taken for the various sub-circuits. So output from the double pole MCB, the live wire goes to different single pole MCBs, and output of the single pole MCBs goes to various sub-circuits. The neutral that comes out of the double pole MCB, it goes to a neutral link. From the neutral link, the neutral wire is drawn for the various sub-circuits. Then we have this earth link. The earth link on one end is connected to the earthing, that may be your plate earthing or pipe earthing, and from the neutral earth link, the various earthing wires are taken out for whichever sub-circuits requires the earthing connection. So the live, neutral and earth wires from the various sub-circuits are then connected to different switchboards. The live wires are connected to the control switches on the switchboards. Finally, connections are made from the switchboards to various appliances and equipment. Okay, so let's now talk about load circuits. So what we have seen is that from the distribution board, we will get a pair of live and neutral wires for each circuit. Additionally, we also get an earthing wire which is normally used for protection. In most cases, the earthing wire is not essential for functioning of the device, but it is very critical for safety. So every load circuit consists of a live wire and a neutral wire. The rule is that all the loads in a single phase installation must be connected in parallel. They are connected between the live and the neutral wires and are supplied at the same voltage. Here's how the connections are made. This is the connection. One terminal of the switch is connected to the live wire. So here you can see that this is the switch. One terminal of this switch is connected to the live wire, which will come from the sub-circuit. The other terminal of the switch is connected to the load. So here you can see that this other terminal will be connected to the load, and the third terminal or the neutral that will come from the distribution board, this neutral will go to the load. Now the earth wire must be connected to the ground pin of all 3-pin socket outlets. This arrangement forms a complete single load circuit. So in this diagram, here you can see that after the energy meter we have the main circuit breaker. After the main circuit breaker we have the distribution board, and after the distribution board this is the load circuit. So in this load circuit you can see that this is the phase and this is the neutral. The loads, these are all loads. So these are the symbols of a lamp and this is the symbol of a ceiling fan. So these are the switches. So you can see that the loads are connected in parallel between the phase wire and the neutral wire. So we have not shown the earthing connections here for simplicity. So now let's discuss the case where we have only one load circuit in a single phase installation. In this setup, the distribution board provides only one pair of phase and neutral wires. Like in this case you can see there is only one pair of phase and neutral wire. All the loads in the installation draw power from this single pair of phase and neutral. This arrangement works fine for a small single phase installations with very few number of load points. However, as the number of load points increases, several challenges arise. First, each circuit connected to the distribution board is protected by a fuse or a circuit breaker. So here you can see that this particular phase and the neutral, this particular circuit is protected by a circuit breaker. So if there is a fault in any part of the wiring, this particular fuse or circuit breaker will trip and this will disconnect the entire supply from this particular load circuit. This is not desirable. Second, as the number of load points increases, the voltage at the furthest point, it will reduce. This is compared to the voltage at the beginning of the circuit. So whatever voltage we are going to get here, and if there are a lot of loads or a number of loads are very high, then the voltage at this point, that is at the beginning of the circuit and at the furthest point of the circuit, these voltage difference will be very high. So this low voltage can affect the output and efficiency of the devices. Finally, combining lights, fans and power points in a single circuit creates additional issues. Power appliances, owing to their large power demand, often cause large voltage drops, which therefore reduces the voltage available for light points. Moreover, faults are more likely to occur in power circuits compared to the lighting circuits. So, what is the solution to the challenges we have discussed? The solution is to divide the single load circuit into multiple smaller circuits. These smaller circuits are called as sub-circuits. Each sub-circuit will have its own pair of phase and neutral wire coming out of the distribution board. All the loads in the installation will be distributed among these smaller sub-circuits. The way the loads are connected in a sub-circuit is similar to how we have seen the connection in one load circuit. Each sub-circuit in turn is protected by a fuse or MCB on the live wire. So you can see that this is the symbol for a fuse. So each of the phase wires of each sub-circuit will be protected by their own fuse or circuit breaker. Additionally, light and fan loads will be assigned to one set of sub-circuits, while power loads will be assigned to different sub-circuits. So how does this sub-circuit solve the problem? First, as each sub-circuit is protected by its own breaker or fuse, so if a fault occurs, only that particular sub-circuit is going to get affected. Rest of the loads in other sub-circuits will continue to operate without any interruptions. So here you can see that we have divided the one load circuit into 3 number of sub-circuits. If some fault occurs in this sub-circuit number 3, this particular fuse will blow, or if there is a circuit breaker, this particular circuit breaker will trip and these loads will get affected. However, this sub-circuit number 1 and sub-circuit number 2, they will not get affected by the fault and they will just work fine as before. Secondly, as the number of loads in each sub-circuit is smaller, the voltage drop at the furthest point now will not be very high. Thirdly, as light and fan loads are separated from power loads, so faults in power loads are not going to affect the light and fan loads. Okay. Now coming to classification, sub-circuits are categorized into 2 categories. Number 1, light and fan sub-circuit, and number 2, the power sub-circuit. So let's look at the light and fan sub-circuit first. So a light and fan sub-circuit, it includes lights, fans and 5 ampere or 6 ampere socket outlets. This means all the lights in the house, all the fans and any appliance or equipment powered through the 5 ampere or 6 ampere socket outlet falls under this category. There are a few important rules for light and fan sub-circuit as per Indian standards. Firstly, a light and fan sub-circuit should not have more than 10 combined units of lights, fans and 5 ampere socket outlets. Secondly, the total connected load in a light and fan sub-circuit should not exceed 800 watts. Thirdly, each sub-circuit must have its own dedicated fuse or MCB for protection. These rules must be followed while designing the house wiring. Now let's talk about the power sub-circuit. So a power sub-circuit includes all the power appliances and 15 ampere or 16 ampere socket outlets. Appliances such as geysers, microwave ovens, washing machines, irons, air conditioners, all of them fall under this category. Any other devices powered through 15 ampere or 16 ampere socket outlets are also included in this category. There are a few important rules for power sub-circuit as per Indian standards. Firstly, a power sub-circuit should not have more than 2 combined units of power appliances and 15 ampere or 16 ampere socket outlets. Secondly, the total connected load in a power sub-circuit must be limited to 3000 watts. Thirdly, each sub-circuit must have its own dedicated fuse or MCB for protection. Now, let's discuss the steps involved in designing electrical wiring for any given case. So, while designing an efficient electrical wiring, several important factors must be considered to ensure safety, efficiency and reliability. Let's go through them step by step. First, we need to determine the number of sub-circuits. For this, we start by assessing the total load requirements. Once the loads are tabulated, they are separated into 2 subcategories: the light and fan category and the power category. Based on the loads, the number of sub-circuits is then determined. However, the final number of sub-circuits may be influenced by factors such as switching arrangements and convenience. It is also essential to provide spare sub-circuits for future expansion. Next, we need to determine the size and rating of the switchboards and the distribution boards. These are primarily decided based on the switching requirements of the consumer and convenience. The size and rating and the number of distribution boards are determined based on the number of sub-circuits, the distance from the load center, and other factors like convenience and restrictions. When the number of sub-circuits is large, it's often more convenient to use multiple number of distribution boards than just one distribution board. Sub-circuits are fed from the sub-distribution board, which is now in turn powered by the main distribution board or other sub-distribution boards. Next step is determining the size of the cables. Cable sizing are essential and a very critical part of electrical wiring design. So if we choose an undersized cable, it may cause insulation breakdown, potentially leading to short circuits. It will also have a higher voltage drop than permitted. On the other hand, if we choose an oversized cable, we have to incur additional costs due to the cost of wiring, the cost of conduits, etc. So this will increase the overall capital cost of the wiring. So the cable size must be chosen based on the required current carrying capacity and the permissible voltage drop. Now, along with the cable size, the breaker ratings must also be determined. It is the breaker which will save the whole electrical wiring in case of any faults. So, choosing the right breaker type and rating is very, very important. So, the breaker rating should be chosen such that it allows the normal current to flow through it without tripping. At the same time, the breaker should interrupt the circuit if there is overload or short circuit detected. Let's understand how to design the wiring of a small electrical installation with the help of an example. In this table, you can see that there are 6 different types of loads. The ceiling fan, the tube light, 5 ampere socket, refrigerator, washing machine, and the 15 ampere socket. So, this ceiling fan, tube light and 5 ampere socket, this particular equipments will fall under the category of light and fan sub-circuits. So here is the table. So you can see that these loads will fall under the category of light and fan sub-circuits. The refrigerator, washing machine and the 15 ampere socket will fall under the power sub-circuit category. So this is table number 2 and these equipments will fall under the power sub-circuit category. Now, the total wattage for each type of load is determined by multiplying the quantity and rating of each device. So here you can see that we can calculate the wattage that will be consumed by each load by multiplying the rating and the quantity. Note that the wattage for the 5 ampere socket is considered to be 100 watts and the wattage for 15 ampere socket is considered to be 1000 watts. So now let's see how to determine the number of sub-circuits. For determining the number of light and fan sub-circuits, first we have to divide the total connected light and fan load by 800. Then we divide the total number of light and fan load points by 10. So we are going to get 2 results. Out of these 2 results, we will take the maximum value. After that, we round it off to the next higher integer. This gives us the required number of light and fan sub-circuits. Similarly, to determine the number of power subcircuits, we start by dividing the total connected power of the loads by 3000 watts. Next, we divide the total number of power load points by 2. Again, we are going to get two values or two results, and we are going to take the maximum of these two and round it off to the next higher integer. This will give us the required number of power subcircuits. So you can see there are two equations that we have used in this slide. So here, this one is as per the connected load, and this one is as per the load number of load points. We are going to take the maximum out of these two, and then this is the rounding up operation. So if you look into the light and fan load table, you can see that there are 8 number of ceiling fans, each with a rating of 75 watts, 8 number of tube lights, each with a rating of 40 watts, 5 number of 5 ampere socket outlets, each with a rating of 100 watts. So the total loads adds up to 1420 watts, and the total load points adds up to 21. Now, as per the rules, in any light and fan subcircuit, the total load should not exceed 800 watts or 10 number of points. Therefore, using the equation that we have discussed before, the total number of light and fan subcircuit comes out to be 3. Now, once we have determined the number of subcircuits, the next task is to divide this 21 number of load points among the 3 subcircuits. While dividing, we must see that the limit of 800 watts and 10 points is not exceeded. There may be different ways to distribute this load among these 3 subcircuits. Like, you can combine loads in a room in one subcircuit, or maybe combine loads in adjacent room in a subcircuit. One of them is shown in the table at the bottom. So here you can see this is one way by which we can distribute the loads. So in this example, each subcircuit feeds 7 load points, with the load on each subcircuit remaining under 800 watts and 10 points. So here you can see the table that subcircuit number 1, the total wattage is 505 watts, which is less than 800, and the number of load points is 7, well within the limit. Similarly, in subcircuit number 2 also, the limits are not violated, and in subcircuit number 3 also, we are within the limits. Now, let's find the number of power subcircuits required for the given example. In this case, we have 4 number of power load points: a refrigerator, a washing machine, and 2 number of 15 ampere sockets, each with a load of 1000 watts. So the total connected load adds up to 3100 watts, and the total number of load points adds up to 4 points. Now, applying the limit of 3000 watts and 2 load points per subcircuit, we can see that the total number of power subcircuit required is 2. Next, the 4 load points must be divided among the 2 power subcircuit. We must ensure that we do not exceed the limit. One possible distribution is shown in the table below. At this point, we need to understand that the distribution may also need to consider many other factors, such as the consumer's required switching arrangement, the location of the loads in the houses, etc. Therefore, the final subcircuit count may have to be modified, but the maximum limit for each subcircuit must not be violated. So, for the given example, we need 3 subcircuits for the light and fan loads and 2 subcircuits for the power loads. Each of the subcircuit will comprise of a phase wire, a neutral wire, and a earth wire. These subcircuits will start from a distribution board. So here is the arrangement. So each one of the subcircuits will require a circuit breaker in the live wire for protection. the live wire of each sub-circuit will start from a breaker. So here you can see that the live wire starts from a breaker and it will terminate in the switches that we have installed in the switchboard. The neutral wire will start from the neutral link of the neutral terminal block and it will terminate in one of the nearest loads from the DB. The earth wire will similarly start from the earth link and it will terminate in the earth terminal of a 3-pin socket outlet. These are the wiring for all the sub-circuits that we are going to see now. So here you can see in the diagram that after the service mains we have the main circuit breaker, and in our given example we will need 5 number of sub-circuits, 3 sub-circuits for the light and fan and 2 sub-circuits for power. So the phase wires will be coming out of the single pole MCBs and neutral wire will be coming out of the neutral link and earthing wire will come out of the earth link. Okay, so this is how the connections will be done. So you can see all the sub-circuits. This is how the phase and neutral are going to supply the various loads.